So the topic that we are going to start today is, the name of the chapter is Polynomials, but in particular we are going to learn synthetic divisions. Along with some other minor topics, this is the main idea that we are going to discuss in today's lecture. Okay, so let's recall a method that we used to use while we used to study in high school. To divide an expression by another expression algebraically. So say we have an expression a0 x cubed plus a1 x squared plus a2 x plus a3, and we need to divide this expression by the linear factor or the linear term x minus h. How do we do that algebraically? This was the idea. First of all, we need to match this x cube and a0 so that we can eliminate a0 x cubed. So in the quotient side, we have to write a0 x squared. That's going to produce a0 x cubed as desired. But we are going to have minus 8 a0. Let's write a0 first. So minus a0 h x squared. That is, we are just multiplying x minus h with a0 x squared. That's all. So now the next step we use to follow is subtract this to get, there would be no x cubed term, right? That was the main idea, to eliminate x cubed. So we are going to get a1 plus a0 h times x squared. And what we do is bring this a2x term here. Then we need to follow a similar approach, find a coefficient and a power of x to multiply with x minus h, so that this term gets cancelled, gets eliminated. Now, for the sake of simplicity, let's just assume that this term inside the bracket is, say, for example, p0. That is, we are assuming p0 equals to a1 plus a0 h. Okay, let's call it p1. I think that would make more sense. So let's just replace this guy entirely by p1. Now, all we have to do, basically, we just replace this guy with a shorter name, and that's all, nothing else. So now, to match with p1 x squared, we need to have p1 x here, so that when multiplied by x minus h, we are going to get p1 x squared minus p1 hx. Again, we are going to subtract so that p1 x squared gets cancelled. Then we are going to have a2 plus p1h times x, and let's bring a3 here. So we are going to follow a similar approach again and consider this term to be p2. So that is, we are considering p2 equals to a2 plus p1h. So let's just replace this entire thing by p2. Now we have to match p2x, so that all we have to add in the quotient side is just p2, so that we get p2x minus p2h. We are at the end of, almost at the end part. So p2x gets cancelled. All we have is a3 plus p2h. And we are going to consider this as p3. So p3 is A3 plus P2H. So just replace this entire thing by P3. And this is the remainder, and this entire thing is the quotient when we divide this particular expression by x minus h. Now, can you see that there is a trend in these three equations? Pi is ai plus ai minus 1h. Pi minus 1h basically. Just consider a naught and p naught to be the same guy. Then we can successfully write pi plus 1 is ai plus 1 plus aih. So not aih, but pih. So we can repeatedly use this expression iteratively, right? We can use this equation iteratively, and instead of writing all these jargons here, we can simplify our task and just use this particular equation repetitively to find the answer. The last pi is going to be the remainder, and before that I have p1 and p2, and we know that the quotient is going to look like this. A naught and p naught are same guy, right? So p naught x square plus p1x plus p2 and so on. So this expression, if this was an n degree expression, if we divided by this linear term, we would start with the power n minus 1 and coefficient p naught and keep going until we get a constant term. So technically, instead of writing all these, we could just directly find expressions. But we can do something which is even simpler if I just find a method to graphically represent the jobs we did here in some convenient way. And let's see how we can do that. So here is how I'm going to present the numbers involved in this calculation. So let's write the numbers a naught, a1, a2, and a3, basically the coefficients of the dividend, right? So, and what we are going to do is look at these expressions and find these expressions and place them in some convenient place in our worksheet. So basically, bring a naught directly here. This is the first thing we are going to do. This is our p naught. Technically, what we are actually writing this row as the AIs and this row as the PIs. But since P naught and A naught are same guy, what I did is wrote A naught in place of P naught. Here I'm going to write P1, but what is P1? We know what H is. So we have an H ready here. Multiply this A naught with that H to write A naught H here, and add these two to get exactly A naught plus A1 plus A naught H, which is basically just P1. Next thing is multiply this P1 by H to write P1H here, add these two to get A2 plus P1H, which is basically P2. Again, multiply this guy by H to write P2H here and add these two to get P3 and so on. And at the last end, the guy at the last end is going to be the remainder, and the quotient is going to be, which should be a function of x, right? It's going to be, start with A naught, and since we are dividing by a linear term, and the initial expression was a cubic, we start with a quadratic term. So A naught x squared plus then we have P1x, then we have P2. So this is the quotient, and the remainder is P3. So this is how we can actually do a division in a much faster way than writing all these on the right-hand side of the whiteboard. So let me show this entire algorithm or whatever it is using an example. So the example looks like this. The question asks, divide thrice x to the power 4 minus x cube plus 2x squared minus 2x minus 1 by x plus 2. So according to what we summarized in our last page, we just do this. Write the coefficients sequentially. This is minus 1, then 2, then minus 2, then minus 1. What we do next, what is h here? Consider this term, compare it with x minus h, right? So we have h equals to minus 2. So we wrote the AI column, now we write the PI column. So 3 comes down directly because A naught is P naught. So just write 3. Then multiply 3 by 8, which is minus 2. So 3 times minus 2 is minus 6. So add minus 1 and minus 6 to write minus 7. Multiply this with minus 2 again to get minus 14. Add 2 and minus 14 to get minus 12. Multiply minus 12 by, okay, I think I made a mistake. If I multiply minus 7 by minus 2, I get plus 14, not minus 14, right? So we have 16 here. Okay. So multiply 16 by minus 2 to get minus 32. Add minus 2 and minus 32 to get minus 34. Multiply it by minus 2 again to get 68. Add 68 and negative 1 to get 67. At the last end, 67 is what the remainder should be. So the quotient is 3. We have degree 4 here, so we start from cube. So thrice x cube minus 7x squared plus 16x minus 34. And if someone is interested to write in the format a equals to qb plus r, then you can just write thrice x to the power 4 minus x cube plus 2x squared minus 2x minus 1 is equal to x plus 2 times thrice x cube minus 7x squared plus 16x minus 34 plus a remainder 67. So this should be the answer, or you can write this as the answer. Please let me know if there is any confusion anywhere regarding the process. All right, so you should be able to realize how fast we got after learning in this new method of dividing by a linear term. But of course, there must be some questions in your mind by now. For example, this should be a valid question. What happens if the problem looks like this? Divide x cubed plus 2x squared minus thrice x minus 4 by 2x minus 1. The entire process dependent on the structure x minus h. This is not in the structure x minus h, right? So what we can do is take 2 as a common factor, factored out of the expression. In that sense, h is half. Now, basically, if we have a equals to qb plus r when we are trying to divide an expression a by another expression b, if the factor here is 2, right? So if you, instead of divide, let's see what happens if we just try to divide by x minus half. That is, take 2 factored out. Is we already know how we can divide by something that looks like this. We know how to divide by x minus 8. So we should be able to divide by x minus half. And let's say this b is that x minus half. So what we did is actually ignored the 2, right? So if you have a 2 here, let's use another color. So if you have something like this, q times b plus r, and if you need to have a 2 here somehow, you need to balance by dividing by 2 here. So if you divide by x minus 8 and get a quotient q, the original quotient must be q by 2. It's as simple as that, and remainder should be as it is. So let's use this idea to solve the problem. So the solution goes like this. The coefficients are 1, 2, -3, -4, and we are using h equals to half as we are trying to divide by x minus half, right? So 1 comes directly here, then multiply 1 by half to get half here. 2 and half is 5 by 2. Multiply 5 by 2 by half to get 5 by 4 here. And 5 by 4 minus 3 is 5 minus 12. So minus 7 by 4, if I'm not making any mistake. So multiply this by half to get minus 7 by 8 here. Then we are going to get 32 and 7, minus 39 by 8, I think. So technically, according to this, the question should look like this. We divided x cubed by 2x minus 1. So we must start from x squared. So 1 times x squared plus 5 by 2 times x minus 7 by 4. Originally, this should be the quotient when we divide by x minus half, but we are dividing by 2x minus 1, exactly double of that. So we need to divide by 2 here in the quotient. And the remainder is exactly what we got here. Remainder shouldn't be scaled there shouldn't be any kind of scaling factor to the remainder. It should be as it is. So remainder is minus 39 by 8. So if you want to express this expression x cubed plus 2x squared minus thrice x minus 4 in this form, then you can just write 2x minus 1 times half, keep that half here, x squared plus 5 by 2x minus 7 by 4 plus the remainder. This is plus the remainder. The remainder is actually negative, so minus 39. Please let me know if there is anything that is confusing you. Otherwise, let me just move. Now comes the next question. We are not going to divide by linear factor every time, right? So a problem might arise that looks like this. Divide. I'm picking the examples from the textbook by Barden, so you can find the exact numerical examples there. Divide 4x to the power 4 plus thrice x cubed plus x minus 1 by x squared minus twice x plus 3. So basically, Generally, when dividing by a linear term, we did not write the divisor on the left because all that mattered was 8. But traditionally, there is a culture of writing the coefficients of the divisor here. So we just write 1 and minus half here. So here we should write 1 and 2 here. You can see that this is the negative of 8. We were multiplying by minus 2 every time, right? So whatever number is here is the negative of 8. So we could, let's not change anything here. So in this case, we can write 1 minus 2 and 3 and divide by this the expression with coefficients 4, 3, 1, and minus 1. But here's the thing, there is a tradition of taking a bracket. You can understand that h is the negative of minus half here. So we discard this minus sign and consider h equals to half here. And we add an extra minus 1 to consider minus 2 as h here. That is why we can take an extra minus, we can just, originally there was a minus 2. Originally there was a minus 2. What we can do is write a bracket here so that 2 and 3 get reversed in terms of their signs. So minus 2 became 2, but 3, there should be a minus here beside 3 so that 3 becomes minus 3. As if we are taking minus 1 factored out of these two guys, right? So what we do is we do a similar process. This is our h. So we multiply by h all the time. So we do something similar actually. So bring 4 here directly and multiply this 4 by 2 to write 8 here and multiply don't do anything with minus 3 yet. So add these two guys to get 11 here. Now do the same with 11. Multiply 11. Let's write 2 here so that it's understandable what the multiplier is. So 11 multiplied by 2 is 22 here. Now multiply this 11 by minus 3. Consider this as the h in the, okay, things are getting messy. I think if I use multiple colors should increase the visuals for you, enhance the visual for you. So 4, give me a moment. Four goes here. Multiplication by, all the red lines represent multiplication by 2. So we get 8 here. And all the blue lines means multiplication by minus 3. So 11 when multiplication by minus 3 produces, give me a moment please. 11 comes here. So let's do it sequentially. So 11 multiplied by 2 is 22. And 4, not 11, but 4 multiplied by 4 multiplied by, not, let's use blue as I mentioned earlier. 4 multiplied by -3 is -12 here. So add these three to get 22 minus 12 is 10, 10 plus 1 is 11, 10 plus 1, yes, 11 again. Not really. 22 minus 12 is 10. Okay, I missed something. X squared term is missing here. My graphics pen is misbehaving. X squared term is missing here. So I just have to make a minor adjustment in the first row. Let's write 0 times x squared here, 1 times x here, and -1 here. So let's get back to where I was. So if you add all three here, 0 plus 22 plus -12, you are going to get 10 here. So we have 10 here. Now repeat the process. You can see that in the last page, when we multiplied by 8, we started from the next place because P naught was A naught, right? Here we did the same for the multiplication by 2. That is, when you multiplied by 4, we started the first person who got after multiplication by 2 is 8 here, shifting by 1. And the first person who got after multiplication by -3 is -12 here, which is right shifted. The starting position is shifted twice, right? 2 place shifted version. So it started 2 place on the right. 2 places on the right. So let's keep going in the same manner. So let's choose red again. So multiply 10 by red line, I mean again multiplication by 2. So multiply 10 by 2 to get 20 here, and multiply 11 by -3 to write -33 here, and add all these three. 1 and 30. 1 minus 33 is -32, right? Plus 20 is -12. Yeah. Okay, just one more place to go. So multiply these 12 by 2 to get -12 into 2 is -24. And multiply 10 by 3 to get 30, so that the sum of the column is, okay, here is the thing. We do not multiply the last guy by 2. So remove this last part. We stop here and add just add -1 and 30. Should it be 30 or -30? It should be -30 because we are multiplying by -3 to get -31. So we start multiplying by 2 from 4. We end at 10. So let's denote those by red mark. These are the ones that are multiplied by 2 here, the coefficient of x, and those who are getting multiplied by these are the same guys who are getting multiplied by -3, but we start writing the red guys from the second position, and we start writing the blue guys from the third position, 1 place shifted. So now you know, if you have one more term, if you divide it by something cubic, you would get one more term here, then you'd get one extra row here for the division, and the multiplication would, the result of the multiplication would, when multiplied by that last constant 4, if 4 was multiplied by that last constant, we would start writing from here, 3 place to the right. So you can, in the same way we proved, give me a moment, please. The way we proved the idea or developed that or constructed the idea of synthetic division of dividing by a linear term here, you can use the same process to construct the synthetic division by a coordinate term that we used here. I'm not showing that because that's actually too complicated to follow, but uses the same technique. So let's just learn how to use the technique instead of constructing the idea, because we already constructed a simpler case. So this is how we divide by a divisor which is of degree higher than the linear term using synthetic division. Please let me know if there is anything that you need to ask, or if there is anything that you have doubt in up to this one. Okay. Now, next example is a bit interesting. We can use synthetic division to solve problems like this. Express the function f of x, which is 4x to the power 4 plus 3x cubed plus x minus 1, exactly the same dividend we used in our last problem, in the form alpha times x square minus 2x plus 3 plus beta x plus gamma times, okay, we have a square here, x square minus 2x plus 3 plus delta x plus epsilon. So you should be able to see that we actually kind of expanded our function in powers of this guy. We already divided this expression by 2x square minus 3. So from last page, we can just write our f of x as, what should be the qx here? The q should be, we are dividing a degree 4 term by a degree 2 term. So we are going to get 4x square plus 11x plus 10. This should be the quotient. And the remainder is not a constant anymore. The remainder is minus 12x minus 31 now. So this is the remainder and this is the quotient part. So our function can be written as x square four x square plus 11x plus 10. So 4x square plus 11x plus 4x square. It's getting impossible to write. 4x square plus 11x plus, I think it was 9, I believe. Oh, 10. All right. Times the divisor x square minus 2x plus 3 plus the remainder, and the remainder, okay, let's just write in plus form. So minus 12x minus 31. Minus 12x minus 30. So this is the quotient and this is the remainder. Now, all we have to do is express this part again in the form somethings times the divisor again, x square minus 2x plus 3 . Now, this is a quadratic term. So if we divide by a quadratic, we are going to end up getting a constant remainder. So just express this part only in this form. So when the multiplier outside here is multiplied, you are going to get something like this times x square minus 2x plus 3 whole squared plus r times x square minus 2x plus 3. After multiplication, you're going to get something like this, and we are going to have the remainder r here or something. This r is a different r, so let's write minus 12x minus 31 instead. So all we have to do is divide this quotient again by the same divisor to express this again in this form, so that the overall structure is exactly what they are demanding here. So let's get to work. We already have done, a big part of the calculation here. So now we have to divide this term now. So the expression is 4, the coefficients are 4, 11, and 10, and we are going to divide by x square minus 2x. It was plus 3, but I took minus as common, so we are getting minus 3 here. And let's do the same process again. So 4 directly gets here. 4 is multiplied by 2, so that we have 8 here. And 11 plus 8 is 19. Now, 19 gets multiplied by 2, but we are not going to continue that because we already reached the situation where we stop, right? So all we have to do is multiply 4 by minus 3 to write minus 12 in this second row, and do not multiply 19 by 2 because we stop here, and 10 minus 12 is actually minus 2. So the quotient comes from here, the remainder is here. So we have, I think, okay, I think, give me a moment, please. Well, we are dividing. This is an interesting situation. This may become confusing for some of you, but you should be able to see that. Let's go to the last page again. The remainder part is here. So in our case, the remainder part is actually here, and 4 is the quotient. So here quotient is 4 and remainder is actually 19x minus 2. And it should make sense because we are dividing a quadratic by another quadratic. So the first quotient has to be has to do something that matches 4x square with x square, and that multiplier is 4. And the remaining part should be because we are dividing by a quadratic term, the remainder should be in generally expected to be a linear term. So now we have to do the replacement here. So we now know what should be replaced. So we have 4x square plus 11x plus 10 to be replaced by 4 times x square minus 2x plus 3 plus, as a remainder, we have 19x minus 2. Now this entire thing has a multiplier outside, which is x square minus 2x plus 3 and an overall remainder minus 12x minus 31. So if you multiply these guys, you are going to get 4 times x square minus 2x plus 3 whole square plus 19x minus 2 times x square minus 2x plus 3 plus a remainder minus 12x minus 31. So this is exactly the format they demanded. We now know that alpha is just 4 and beta is 19, gamma is minus 2, and delta is minus 12, and epsilon is minus 31. So let's do something that helps us to make this. The problem actually required whatever we did in our last page to solve the last problem. So the new problem here requires the solution of the last problem. Can we do this two-step problem solution converted into a single-step problem? Let's see. So we can just do this. Copy this table entirely from here. So 1 minus 2 minus 3, 4, 3, 0, 1 minus 1. 1 minus 2 minus 3, divisor part. And we have 4, 3, 0, 1 minus 1. 4, 3, 0, 1, and minus 1. And we have 8, 22, and 20. 8, 22, 20. Minus 12, minus 33, 30. Minus 12, minus 33, and 30. So that when added, we got 4, 8, 10, minus 12, and we got minus 30 there, so minus 31. Okay, now this part was the remainder, and this part was the quotient. And you can see that this quotient is the expression that we divided by the same divisor again the next time. We have exactly 4, 11, and 10 here. We have 4, 11, and 10 here divided by the same divisor. So all we have to do is continue the process for this part of the this region only, the quotient sign. So we can just copy from the last page, 8 and minus 12, that's all. So we have 4, 11, and 10. I wrote, okay, this should be 11. So only 8 here and 12 here, I think. minus 12 here. So continue this. So we have 4 here, 19 here, and minus 2 here. So this is the quotient and this part is the remainder. And we can express this entire expression from this row, this part only. So we can just write 4 times the divisor square, the divisor being this guy, right? The divisor being x square minus 2x plus 3. So 4 times divisor square plus, now get here, to get 19x minus 2 times divisor, then get here to get minus 12x minus 31. This is the exact expression we got, but now this, if we merge the two steps together, this becomes way faster, and you can just pick up the exact numbers from the remainder rows, right? So this makes things faster and easier. Let's use the idea we just collected to solve the next problem, which goes like this. Express, let's use another, express 2x cubed plus x squared minus 5x minus 3 as a polynomial in x minus 2, but not in x. It's already in terms of x, but we want to express this or rearrange this so that it becomes a polynomial in the variable x minus 2. So technically, we are dealing with a problem that looks like this. We are being asked to express this guy as something like, if this is considered as d, we need to express this guy as ad cube plus bd square plus cd plus e, that is in expansion in powers of x minus 2 only. This is what we are being asked here. So we just follow the process we developed in while solving the last problem. We have the expression 2x cubed plus x squared minus 5x minus 3, and we need to divide by x minus 2. So h is just 2. So let's start the process. So 2 comes down directly. Multiply 2 by 2 to get 4 here. So we have 5. Multiply 5 by 2 to get 10 here. So the 10 minus 5 is again 5. Multiply 5 by 2 to get 10 here. So 10 minus 3 is 7 here. And we understand that this 7 is the remainder and this part is the quotient. And according to the knowledge we collected in while solving our last problem, we now know that we need to continue dividing this quotient by 1 minus 2 again. So 2 comes down directly. Multiply 2 by 2, we have h equals to 2. So multiply 2 by this h to get 4 here. So we have 9. Multiply 9 by 2 to get 18 here. So we get 23. So this is the remainder, and quotient side is this side. So divide by 1 minus 2 again. So 2 comes down directly. Multiply 2 by 2 to get 4. 4 and 9 means 13. So this is the remainder. So now we know that this is the final quotient. So this guy is just 2 times x minus 2 whole cube plus next remainder is 13. So 13 times x minus 2 whole square plus next remainder is 23. So 23 times x minus 2 and last remainder is 7 plus 7. So this is the expression. If you expand this expression, you will get the same that was given, the same expression that was given in the question. So this is a pretty fast process to express a polynomial in powers of some other linear term than x itself. So synthetic division is pretty helpful and useful. That should be evident by now to you, right? Please let me know if there is any confusion. Sometimes we can do problems that are not apparently related to synthetic division at first. For example, if f of x is 2x cubed plus x squared minus 5x minus 3, find f of x plus 2. So they're asking to replace x by x plus 2 and find a simplified expression. This does not call for synthetic division, but we can use synthetic division to actually solve the problem. So what we can do, basically, you can see that the expression I use here is the same expression that was getting divided by x minus 2 in the last problem. So the solution can go like this. Solve the last problem to get the result that f of x was simply 2 times x minus 2. Basically, divide by x minus 2. Even though they asked for x plus 2, divide by x minus 2. You should be able to see why in a moment. So 2 times x minus 2 whole cube plus what was the next 13, 23, and 7. All right. So 13 times x minus 2 whole square plus 23 times x minus 2 plus 7. So now you can see that replacing x plus 2 became just easier. It's just 2x cubed plus 13x plus 23 plus 7. So all you had to do is just do the same synthetic division, and that took less than 2 minutes, I think, since we are doing everything by following a pretty fast algorithm. So this is how problems of these kinds can be solved using synthetic division. And we can solve problems like this one. For example, express x to the power 4 plus thrice x squared plus 2 in the form a plus bn plus cn n plus 1 plus dn n plus 1 n plus 2 plus en n plus 1 n plus 2 n plus 3. Now you could use just different value. Okay, I think I mixed up two variable names in the question. So give me a moment. So replace x by n in the main question. Okay, so you can do this. You can consider this to be f of n and find f. This is the same f of n here, of course. So put we have how many unknowns? A, B, C, D, 5 unknowns. So put 5 different suitable values of n to get 5 equations in these five linear equations, actually, in these 5 variables, and then solve the 5 equations simultaneously. But that's going to be pretty tiresome, right? But you can do whatever we learned in our last few problems. We can use them. For example, the expression n to the power, the coefficients are 1, 0 because n cube is absent, 3n square, n is absent, and 2, and divide this by 1. The first coefficient that we need to find is, give me a moment, please. So divide by n plus 1 first. So 1 plus. This is because if you divide by, the factors are n, n plus 1, n plus 2, n plus 3, and n plus 4. But if you divide by n, you are going to get remainder of 2. That's visible to you. That is why let's start by dividing n plus 1. So we get 1 directly here, multiply 1 by minus 1 because h is minus 1. So minus 1 gets here. So 0 minus 1 is minus 1. Multiply by minus 1 to get 1. 3 plus 1, 4. After multiplying by minus 1, you get minus 4 here. So we have minus 4 and stop here. Because these two is already, actually we skipped a step. Actually, the first divisor had to be n. But we already know what the divisor should be when we divide by n. So this 2 is already the first remainder. We skipped a step by the step of dividing by n. So now you have to divide. This is a remainder, right? When divided by n plus 1. So divide by n plus 2 now. So 1 plus 2. So 1 comes down here, multiply by minus 2. So minus 3 should be here. Multiply by minus 2 to get 6. We should have 10 here and stop. And this is the remainder for this step. Then multiply by n plus 3. This is the last division. So 1 comes down directly, multiply by minus 3 to get minus 3 here. We have minus 6 here and stop. So basically, the last divisor actually, the last quotient is actually the quotient when we divided by all the divisors, n, n plus 1, n plus 2, n plus 3. So this is actually E. So this 1 is actually E. So the first term should be n into n plus 1 into n plus 2 into n plus 3, and the coefficient is 1 here. Then comes minus 6, right? So minus 6 times n, n plus 1, n plus 2. Then comes 10 plus 10, n, n plus 1. Then comes minus 4, minus 4, n. And the final remainder is the constant term plus 2. So we use the same technique, but in the last cases, we had to divide by the same divisor because we had to express in powers of that divisor. But here, the divisor changed at each step, right? So this should be the answer. All right, let's move on to our next example or next problem. This is the last problem from this topic. And the problem goes like this. I have one more class after this. I don't know how I'm going to conduct that class. So if f of x is equal to thrice x to the power 4 plus 2x squared minus 6x minus 4, find f of 0.2. This should be interesting. Basically, there is no symptom of synthetic division anywhere here, right? But can you recall that if you divide a function by x minus a, then what should be the remainder? Can you recall remainder theorem? Can anyone tell me? If you divide f of x by x minus a, what should be the remainder? Can any of you tell me? All right, you should have remembered that if you divide an expression by x minus a, the final remainder is actually f of a, because if f of x is expressed as something like this, then putting x equals to a gives you f of a equals to 0 times whatever q of x is, doesn't matter, plus r. So the remainder is just f of. So f of 0.2 should be something that comes out as a remainder when you divide by 0.2. So just use synthetic division to divide this expression 3, 2, minus 6, minus 4 by 1 minus 0.2. So h equals to 0.2 here. Continue the process, and finally you'd see that the remainder comes out as minus 5.1792. I'm not going into the detail of the problem. So this is the this is actually f of 0.2. So I think that would be all from synthetic division. I'm going to teach one more topic in today's lecture, and that topic is related to polynomials in 2 or more variables. So polynomials in 2 or more variables. Okay, so generally, we're going to actually only focus our concern to quadratics only. So a quadratic polynomial in one variable looks like this: ax squared plus bx plus c. Generally, it looks like this. So this is polynomial in one variable. But if we have a polynomial in two variable, a quadratic polynomial, the most general quadratic polynomial in two variable looks like this. Ax squared plus by squared plus 2hxy plus 2gx plus 2fy plus c. Now we are interested in factorizing this quadratic into two linear terms. So we want to assume that this guy is actually equal to some px plus qy plus r times p prime x plus q prime y plus r prime. So basically, what we can do is, I'm not going to do all the rigorous calculations, but what we can do is, let me state the steps that we need to follow to solve the situation. That is, multiply these twos and equate coefficients of individual terms from each side, and solve for PQR, P prime, Q prime, R prime. And since there are 6 terms, there has to be 6 equations after equating term-wise coefficients, right? So 6 unknowns, PQR, P prime, Q prime, R prime. 6 unknowns, 6 equations, you should be able to find a solution. I'm not going to solve it, but I'm going to mention a condition that needs to be true so that you can actually factorize this, because not every polynomial that looks like this in polynomials, quadratic polynomial 2 variable, can be factorized into linear factors like this. There is a condition actually. The condition is, there is an expression called the discriminant, and expression of the discriminant looks like this: ABC plus 2FGH minus AF square minus BG square minus CH square. And this is factorizable if and only if delta is 0. That is, this expression or this discriminant is equal to 0. If this discriminant is not equal to 0, you cannot factorize a quadratic polynomial two variable into two linear terms. Now, a question might arise. Some of you might wonder, why is it not possible to factorize every quadratic polynomial two variables? Let me answer this question not algebraical perspective, but from the geometry perspective. And a quadratic polynomial equal to 0. If you write an equation like this equation represents what? In 2D geometry, this equation equal to 0 represents what actually? It represents, depending on the coefficients, it may represent circle, it may represent an ellipse, maybe parabola, maybe hyperbola, and none of these can be represented if you can just factorize them into two linear factors. Because if you equate this guy to be 0, then you are going to get two equation of straight lines. One, this equals to 0, the other one, this equals to 0. So you are going to get a pair of straight lines. That's the fifth possibility. So there is a fifth possibility, a pair of straight line. So, so basically, if you draw this expression for different choices of A, B, C, H, G, F, you are going to get different kind of shapes depending on the choice of the coefficients. And it's evident that you are never, it's not going to happen that you are going to get a pair of straight line every time. Sometimes you have to get something like a parabola or an ellipse or a circle sometimes, right? So that means if this was possible to factorize every time, you would get a pair of straight line every time, right? So that's not the case. So this just kind of geometrically proves that this algebraic expression is not factorizable into linear terms every time for every choice of coefficients. So this is called a discriminant that makes sure that if this is 0, we are sure that it's going to be factorizable, otherwise it's not. And that would be all. This is the last idea that I wanted to teach in today's lecture. If any of you do not have any more question from anywhere on the top of the topics I talked to in today's lecture, I'm going to close the meeting. All right, okay, let's stop the recording first and then close the end.